All right, Science Peeps, Mr. McCloud here. I wanted to give you a decent video that wasn't just me talking on Zoom or whatever, and talking about the kinematic formulas, the different forms of the kinematic formulas, and then I'm going to show you how I derive the big one, the big shebang, the one that has all the variables. And then we're going to derive one extra one, a fifth formula. We call that one the time-independent formula. Basically, it takes the things that we need to know elsewhere, it gets rid of time, which, if I'm sure you would agree, would have made the problem I gave you earlier a bit easier. Now, it is possible to solve the problem that we were working on earlier in class without this fifth formula, but it basically takes one step out. Instead of doing a system of equations like we kind of have to do, instead we can do one equation to solve it all. But we'll get to that at the end. Plus, I'll throw in a little calculus at the end to help those who want to kind of know the calculus reason for this, the way Newton came up with it. We'll do that. So that's what you're looking forward to on this video. Anyway, I'm not going to be solving any specific problems. That'll be video 2, the next kinematics video. But I kind of want to do basic here. So once again, if you guys remember, delta x equals x final minus x initial. This is our displacement formula. Then we have our second one, which is our velocity formula. And our velocity is called velocity because it has a direction. And how do we know it has a direction? Well, it has the displacement formula built into it. And that means our displacement is going to be positive or negative. Okay, so displacement formula, delta x over delta t. Acceleration formula is when we have a changing velocity. That either means velocity that is increasing or decreasing. And it all matters on perspective. A decreasing velocity in one person's perspective, flipped around, is an increasing velocity. And so we have to identify what is positive and negative before we start. But we've talked about that. So those are the three main ones. And then once we start combining them, you get this big buddy right here. Delta x equals velocity initial times time. If you notice I made that mistake in the work previously, I forgot the time variable. Now it's back in there. And I'm going to put little brackets around that so we know that these are all sort of a function of time, right? If we're thinking of functions. Anyway, so there we go. And yeah, the first thing I'm going to do is I'm going to take equation 2 here, this velocity formula, and I'm just going to rearrange it into 3 different ways that it can be arranged. We already have version 1, velocity equals delta x over delta t. Version 2 just means I am moving delta t to the other side of the formula, so just multiplying both sides by delta t and bringing it over here. And so in that case, delta x is what we're solving for, is equal to velocity times delta t. Now, I'm not insulting your intelligence here, so all of you could do this. But I like to sort of write it out so that way when you're doing something more advanced, you can look at this and be like, oh, I should use that one. It helps a little bit. All right, and then last but not least, we need one that solves for time. We have one that solves for velocity, one that solves for delta x, and now we have one that solves for t. So to solve for t, we just need to move velocity back to the other side of the formula, back over here. So divide both sides by velocity. And in that case, delta t becomes, well, if that moves over there, becomes delta x over velocity. So our distance divided by our velocity is our time. Seems a little backwards, but that's what it is. I'm going to try to write this real nice so we get a nice, clean picture of it. All right, so 3 different ways of arranging this that make it useful. Third one, our acceleration formula, we can do the same thing with. We're actually going to need to do this to solve the big boy over there. All right, acceleration equals delta v over delta t. I'm going to multiply both sides to solve for velocity. So we get another solution to this is delta v equals acceleration times time. Pretty straightforward. At equals delta v. And last but not least, we're going to also move acceleration to the other side of the formula, and we're going to create a version of this that solves for t. So t, time, is equal to delta v, velocity, divided by acceleration. Boom. Okay, now we have 3 versions of this formula. In all reality, we're just rearranging the formulas. But here they are. Now, I'm going to show you a quick cheat that we use in general physics. I don't expect you guys to need to use this because most of you are doing advanced mathematics. But let's say, oops, I drew a circle, I need to draw a triangle. There's a cheat triangle is what we call it. So if I draw a triangle, and if I put delta x up here, so delta x, and then below I put v and t, the way this triangle works, sorry if you can't see that very well, let me draw it just a little bigger. So delta x, v, t. Okay? You're going to see why I do it in this order here in a second. Like I said, this is just like sort of a cheat triangle. This is a terribly drawn triangle. There we go. And there we go. Alright, so the way this triangle works, and there's a line here splitting these two variables. Remember, this is delta t. The way that this triangle works is whatever I'm looking for, if I put my hand over it, whatever's left is how I find it. So it's like, if I'm like, I need to find velocity in this formula, I cover velocity, what am I left with? Delta x divided by delta t. If I'm looking for time, and that matches here, right? If I'm looking for time, it's delta x divided by velocity. Okay, look at that. And if I'm looking for distance, it is velocity times time. Since they're next to each other, we just assume there's a time symbol there. And we could make one of these for acceleration as well. So if I did that, it's another triangle here, a little bigger. And I don't expect you to use this. This is AP Physics, so I just want you to know that this is how we get people who have a little trouble remembering the formulas to quickly get solutions. So it might be a shortcut for some of you. I don't know. So once again, whatever I want to know, I cover up. And it actually builds these three formulas. Just a quick cheat there. One of those doesn't exist for this. So don't worry about that one. Anyway, so that was my first promise. I've expanded these, I've made them simpler, so now you can see each one of them. My next promise I want to complete is I want to show you why this is the formula it is. Because I don't want you to just trust that, hey, I somehow combined these two and called it a day, and it worked. I want you to actually see the data. So I'm going to take the black marker here, because I like to draw lines with the black marker. All right, and I'm not going to keep this up the whole time, because I'm going to need this space here a little while. So I'm going to prove it, and then I'm going to erase it. So if we want it, take a quick snapshot if needed. All right, we're going to use this as our velocity axis, and this is our time axis. So, and the reason I have a velocity time axis is I know I'm solving for acceleration. And if you guys look at velocity over time, this is the rise over the run on this graph. The y-axis divided by the t-axis, well, the slope of that is acceleration. And so we're going to need that. So let us pretend that we don't have any acceleration first. Let's pretend that. Let's pretend I just have some velocity, and I do it for some amount of time. So we're going to say, we're going to call this t final. We're going to call the starting point t initial. And we just want one velocity, so we have no we have no velocity final. We just have the velocity, so v, and I'll just call it v sub a. We'll call that for absolute velocity, never changed. All right, so here's my question. If I wanted to use this graph to find distance, not acceleration, we're not worried about slope. Acceleration will be 0 because the rise over the, look at the slope. What's the slope here? Slope is 0. V over t, 0. That's not the problem here. I want to know is, can you tell me distance? Can you tell me displacement? Can you tell me how far we went using this graph? Well, if we look at our velocity formula and we look at it, we can see that velocity times time equals displacement. So basically, if I take this side of this square or rectangle and I multiply it by this side of the rectangle, the area of this rectangle, a little geometry here, is going to give me my distance, my displacement. So this one graph can not only tell me acceleration, it can also tell me displacement. So let's write a formula for that. It's going to be, well, it's 0 to v. So we're just going to write VA minus 0, because remember this is just delta V. So it's delta V times delta T, and delta V doesn't have a delta. We stayed at the same point. So really this is just going to be V, right? V times T. And what does that equal? Well, that's going to give us delta X. All right, so we're going to call that equation 1 for the situation. Now, let's say instead of a constant velocity, I want something with an acceleration. I want to know how far I went if we had a constant acceleration. Now we're going to practice this more, but you can tell it's a constant acceleration when the line is diagonal and has no like curves to it. Basically meaning that the rise over the run every few seconds that goes by remains the same amount. The slope is the same. We don't have constant velocity here, but we do have a constant acceleration. And by the way, this formula only works if we have constant acceleration. Changing acceleration, we have to do something far more complex. Something you wouldn't do in AP Physics, or probably in your first couple years of physics at university. So don't worry about anything but constant acceleration at this point. It's one of those things that we tend to work on. Now, what is the area of this shape? Well, it's the shape we had before. Now remember, I didn't use any numbers intentionally. This is just me creating a proof. Well, we have that already. But now we have to add this little triangle. Plus, well, if we have this little triangle, and we had this pretend starting velocity, well now this triangle ends at an actual ending velocity, right? Velocity final. We now have a change, right? Between these 2 points. And we're going to call this VI now, just because it's now technically an initial. So we have a starting velocity. Now, if this was 0 down here, then we just get rid of this part. But sometimes we need this part, right? Because we may not start at 0. We might start somewhere up here. Anyway, so we're going to use the same concept that the area, velocity times time, is going to give us how far we went. And of course, we had to add it to this other piece to make that possible. So let's do it real fast. Well, first it's the triangle. So I know the area of a triangle is 1/2 base times height. So it's going to be, equation 2 is going to start with 1/2. Okay, got the 1/2 down. Base is T final minus T initial. So I'm just going to do delta T. Right? And then we're going to go V final minus V initial, or delta V. Delta V times T. Now we know that's distance already. Delta V times T, that gives us distance. But I want to know, if I just combine these two formulas, we would kind of just get we might actually do that. We'll do that a little later. You actually get a useful formula if you combine these two. But right now, I want an acceleration, time, velocity, distance, or displacement formula. I want all the variables in one spot. The perfect formula for these situations. And so what I'm going to do is I'm actually going to replace delta V, going over here, with this version of delta V, where delta V equals acceleration times time. By the way, this should be change in time, right? Keep forgetting that. So I'm actually going to plug in a delta T, not because I couldn't plug in something else, but just because I know there's an acceleration, I want acceleration to be part of the problem. So by replacing delta V here with this formula, by just plugging it in, we get 1/2 a delta T times, well, there's already a delta T there, so delta T again. And so what we get is 1/2 a delta T squared. Now, if we add these two formulas together, you can probably already very quickly see that this part right here is this part of the formula, and this part right here is this part of the formula. And so we have, in fact, recreated the projectile motion, the parabolic motion, whatever you want to call it, the full formula for kinematics for equation 4. Now, like I said, this is the algebraic explanation. It is the best way to explain it algebraically, You may have felt uncomfortable when I just picked an arbitrary point. That's just because I was trying to make a generic formula with no numbers, just with variables. Now, really quickly, I'm going to erase this. So take a snapshot if you want it. This proof. I'm going to erase this. Okay. And I'm going to erase this because we already have it all up here. It's already in one spot. So don't need it anymore. Boom, boom, boom. And I'm actually going to grab this because I want it to be a little cleaner. There we go. Now, what about the calculus version of this? Well, with the calculus version, we start at acceleration. We say, if we have an acceleration, if I have an acceleration, I know that acceleration is the slope of a velocity time graph. So let's say we have this line here. I know it's the slope. So by the way, we're going to have some non-calculus at the end here, but I just wanted to throw this in real fast. So watch anyway. It could be interesting if you're not currently in calculus. So anyway, this slope is acceleration. And so because the slope is acceleration, if we know what acceleration is, let's say acceleration is 10, well, how would we figure out what the integral of this is? What if we're going backwards? What if we're trying to go from the slope, or the derivative, backwards to find velocity or time? Well, in that case, we would have to take the integral of the variable acceleration. So, to do that, we say the integral of acceleration with respect to time, so dt, a dt, is equal to, well, you probably know what this is already. It's acceleration times the variable, times t, at, and it's plus some constant, right? Now that constant's going to be important. So instead of c, this is going to give you a hint where we're going with this, we're going to call that constant v. And in some circumstances, you could set this equal to 0. And so you could rearrange and say a times t equals negative v, or really we're dealing with absolute value situation because we don't really know what these numbers actually are. But a times t plus v, which remember, it's just a constant at this point. And if you had acceleration and you wanted to know velocity, well, velocity would be for each moment you picked, it would technically be like a constant at that moment. But don't worry about that. That's complicated beyond what we need. So now, what if I were to take the integral of this? What if I want to know the area under the velocity? What if I wanted to know the area under the area under? So basically, if we take the derivative of acceleration and time, we get, acceleration time velocity, we should get acceleration, v should disappear with respect to time, right? But if we take another integral, what do we get? Well, if you take the integral of something that's already been multiplied by its variable, you're going to get a dot t divided by 2, and you're going to get plus, well, you're going to take that previous c value and multiply it by t, and then you're going to add another constant. And in this case, you can probably guess that that constant actually represents our displacement. Now, if I just, and by the way, you had to square the t, right? That when you do that, you bring the 2 down, but you got to it's the rule, right? So there we go, and that's the function y, right? Let's just call it the function y at this point. So at squared plus vt, and if we want to, we can rewrite that divided by 2 just as 1/2, right? And basically, we just recreated this whole formula again, but we could technically move the x over there to the other side. And so that's the calculus version of this. And Isaac Newton invented this specifically because when dealing with the other way, if we were dealing with distance and time, and he dropped an apple, or he watched the moon orbit the Earth, or he watched how the planets orbit the sun, he would get curved paths. And the problem with this is he literally invented calculus to solve this problem. And he wanted to find what the derivative was, or the slope of this line is, to find velocity, and then taking the second derivative to find acceleration. And yeah, works forward and backwards. Anyway, quick calculus explanation, probably not the most scientific or mathematical version of this explanation, but I wanted to throw it in there for you guys that want to do it. All right. Cut back. If you were watching the video, this last part is a very important formula, and that is formula 5. Okay, and formula 5 is a combination of formula 4 and formula 2, or it's really 2, as you were. It's formula 3C. There it is, 3C. All right, so basically, let's say I want this formula, but I want one that has no time involved. Finding time was such a pain. I didn't want to do the quadratic formula because, as you see, this is set up as a quadratic. So what do? Well, what I do is I replace t, I solve for t in the acceleration formula. Well, we already did that. That's one of these versions we came up with down here. So we got t equals delta v over a. And so I'm going to plug in delta v over a for all my t values. So rewrite this, delta x equals vi times, well, I'm replacing t with delta v over acceleration over a. Okay, and these are all vectors, right? And so that's instead of time now. And we're going to add to that plus 1/2 a. Well, once again, we got to replace t again with delta v over acceleration time, squared, right? Because we square the time, so we're going to square what we plugged in there. I'm going to switch pins here. This pin is a little too small. I like it. I want it to stand out. So here we go. Let's start simplifying this madness. So delta x equals, well, vi times delta v. We'll just, for the moment, we'll just say vi delta v divided by acceleration plus 1/2. Okay, now let's simplify this side. 1/2 a times delta v squared over a squared. Delta v squared all over a squared. And before I move on, I'm actually going to simplify this. We have a out here, a squared on the bottom. Let's get rid of the square, get rid of a out here. And really quickly, you're probably noticing, since these are multiplied, so we'll just start down here. We'll write 1/2 times that. There's a reason I haven't multiplied that in there yet. You'll see it in a minute. But both of these have a on the bottom. Both of them have acceleration. So because of that, we can pull acceleration from both of them as 1 over a, and we can multiply that to the other side. And what we get is we get a delta x equals vi delta v plus 1/2, we haven't lost the 1/2, delta v squared. And that's it. There we go. All right. This is still too complicated. There's so many things in here that can cancel out. So we're going to make that happen next. So a delta, well, I'm just going to work off of this one, so I don't want to run out of space here. So vi delta v is the same thing as vi times v final minus v initial, right? Delta v is just v final minus v initial, plus 1/2 v final minus v initial. Well, because it's squared, I'm going to write this twice, v final minus v initial, and we have to then have this binomial, right? We have to multiply, we have to do the whole thing, right? The whole thing we normally would do in a quadratic situation. So I'm going to simplify this. V final times v final becomes v final squared. Negative vi becomes vi squared. And negative vi times vf, the bottom part, plus the other bottom part, becomes negative vi vf and negative vi vf, which becomes negative 2, I'm going to space this out a little bit more, vi vf, and remember that was at the end plus vi squared. I just erased it there for a second. And then what I'm going to do is I'm going to actually distribute this 1/2 into all of that. So divided by 2, okay. This one already has 2 in the front, so dividing by 2 just gets rid of the 2 in front. And then this one divided by 2. And then in front here, let's distribute this into there. We get vi vf minus vi times negative vi. So it becomes minus vi squared. And then there's a plus between these guys, right? Let's simplify it even more. We have a vi vf here, and we have a negative vi vf here. And because everything's being added and subtracted, we can just combine those right off the bat, getting rid of both of them. Let's do that. All right. And then we have a positive vi squared over 2 and a negative vi. And so because we have a positive half of a vi squared, if we were to add that to this total vi, which is the same as writing 2 over 2, right? That's one whole. We're going to end up with a negative vi over 2 if we combine those. So this goes away. So negative vi squared over 2 equals a times delta x. Okay, we're almost done. Right at the end here. You can already see what we're going to do. We're going to take this 2 on the bottom of these, pull them out like we did previously in that other portion as 1/2, and bring the 1/2 over here. And this becomes 2ax, right? So those go away. And then the last step is I'm just going to switch these places because I want it to be vf squared minus vi squared. And that is, at the end of the day, our final formula for this. So as you were, minus vi squared equals 2a delta x. And what did we create here? What have we done through all this crazy algebraic nonsense? We have created a formula that has acceleration, displacement, and velocity, but no time variable. So if you guys were imagining that rocket problem we did earlier where the rocket's going up and then the fuel cuts off, what we had to do before is we had to solve for time using this formula and a known final velocity, or initial velocity, and then we had to plug that value into here and then run this whole formula to solve that. But with this version of these two combined, it does that for you. You just take our final velocity, well, with your rocket going up, your final velocity is just going to be 0. Your initial velocity, which I believe when we discussed it ended up being like 80 meters per second, square that, move the 2 over, move a over, which remember a is 9.81, it's gravity in this situation, and that would give us the elevation we went. Much simpler, much easier, but a lot harder to prove than everything else. So to finish this up, because I want to take a snapshot of this and sort of put it into our notes, right? I'm going to erase all this. This isn't the best thing for me to keep anyway because I erased as I went. Chances are if I wanted to do this and have it all be on one, it would take up the whole whiteboard and we wouldn't have any room for anything else. So what we end up with is, we end up with v final squared minus v initial squared equals 2 times acceleration times delta x. And this is equation 5, but really it's just a combination of equation 4 and equation 3. And by the way, the proof I did earlier, equation 4 is really just a, a manipulation of equation 3 and equation 2 being combined. So these two are kind of the big ones, but they're made up of these already. So they're logical. They're not just something that just randomly happened in nature. They're actually derived. Anyway, that's pretty much it, except for there's one thing I never talked about in class, and I'm going to put it on here, but we will talk about it in the future. G is our variable for gravity. G equals acceleration due to the Earth. I'll put a little e down there. And we accept 9.81 meters per second squared. And the AP exam sometimes will round this to 10 to make your life easier on the fly. But I just want you to know that if you see that I, in our work, have replaced A, all these A's, all these accelerations, with G, it's because G, we call this little g, there is a big G. We'll get to that later this year. That's the gravitational, universal gravitational constant. We're going to talk about little g a lot though. Little g, we could replace some of these, but is it always gravity? No, sometimes we have a rocket pushing up, or we have a person pushing a car or something. Acceleration doesn't have to be gravity, but in this situation, if it is gravity, this is it, and this is the variable we use. Anyway, that was a bit long, but hopefully this creation is useful for you. I will talk to you guys later, and I will post this video as fast as I can. Have a great day. Mr. McCloud out.